In this video, we're going to finally see how to calculate a derivative for pretty much any function. And so, the idea here is we're going to use the derivative as a limit. And if we recall, if I want the average slope, or the secant slope, the slope of a secant line, you can just use the difference quotient. So f of x plus h minus f of x all over h. And so looking at this, we have two functions and two separate points. I can have a rise, which is distance from here to here, and a run. But now the question comes in, how do I use an average slope to find a tangent slope? So here's the idea. The derivative at a point will be f prime of some x value, x naught, will equal the limit as h approaches 0 of f of x naught plus h minus f of x naught all over h. And the idea is this. So we saw our tangent line, our graph with our secant line, and we had 2 points and the line through them. And clearly this isn't the tangent line, it sort of crosses through the curve at an angle, and we have this point, this x value, x naught, and the distance to our next x value is h, so that gets me here, which is x naught plus h, and this is just slope formula, going from the point here, which is x f of x, to the point here, which is, x naught, f of x naught, to the point here, which is x naught plus h, f of x naught plus h. Okay? And here's the trick. I want to try to see what happens at an instant, not over some interval. And so what I can do is this. I can try to move my points closer and closer together. And as I move them closer together, you can see this line gets closer and closer to what the tangent line should be. But there's a problem. Once I get them one on top of the other, I can't actually do slope formula, because that would give me the rise of 0 and the run of 0, and 0 divided by 0 is undefined. Okay? So the trick to do it is with this limit. I want to see what the limit of this line is as I move these points to being one on top of the other, but I can't actually get there because that would be a 0 divided by 0 slope. Now, that is for a derivative at a point. Our derivative is a function, so the derivative function, instead of considering a specific x value, we'll just consider any x value. So f prime of x is equal to, the limit as h approaches 0 of f of x plus h minus f of x all over h. Now there are some equivalent ways to deal with this, so I could also look at this as the limit as h approaches 0 of f of x plus h minus f of x minus h all over 2h, which instead of starting somewhere and going right, actually goes to the right and to the left, and then squeezes the points in, and this limit will equal that limit everywhere that the derivative exists. Or I could also have this, the limit as a approaches x of f of a minus f of x over a minus x. The trick to all these is I'm moving 2 points closer and closer together and considering the slope between those. So let's see a couple of examples. Our first example is this. I want to find f prime of x given this function. And so all I do is I jump right in and say, okay, f prime of x will equal the limit as h approaches 0 of f of x plus h minus f of x all over h. Now I'm going to try to fit this all in here. These problems can sort of whir out of control, but I should have enough space to finish this off. So that's going to equal, I put x plus h into here, so let me do some color coding here. So f of x plus h, I will have x plus h quantity squared minus 2 times x plus h plus 3. And then I have a minus, and now I just do f of x. So I have x squared minus 2x plus 3 all over h. And don't forget the limit. This limit should not disappear. It doesn't just magically disappear and reappear. It's there throughout. I'll expand out all of this. So I have the limit as h approaches 0. Expanding out this, I get x squared plus 2xh plus h squared. Distributing the negative 2, I get minus 2x minus 2h plus 3 minus, and here I have x squared minus 2x plus 3 all over h. And now a lot of stuff cancels. The x squared minus x squared cancels. Negative 2x minus negative 2x cancels. And 3 minus 3 cancels. And so I'm left with the limit as h approaches 0 of 2xh plus h squared minus 2h all over h. And I can look at this one of two ways. Either I can consider factoring out an h in the numerator, so I have the limit as h approaches 0 of h times whatever's left over, 2x plus h minus 2, and those cancel. Or I can just say, okay, everything has an h in it, so I can divide out an h from everything, and either way I do it, I'll get to the limit as h approaches 0 of 2x plus h minus 2. H is approaching 0, so this will just equal 2x minus 2. Alright, on to example 2. Now this one is very similar, and eventually we will have a shortcut for it. So I do want to point that out. There are shortcuts to find the derivative function much easier, but they're all based on sort of patterns that get picked up from this limiting process. So let's dive right into this. I need two things to find these equations. I need the point, and the point is as easy as just evaluating y of 1, which is going to be 1 cubed minus 4 times 1, which is negative 3. So this means that we go through the point 1, negative 3. And I need the slope. And for the slope, I'm going to do pretty much the same thing I did before. So I need to find out what dy dx is. And that's going to be putting x plus h into the function. So I have x plus h cubed minus 4x plus h, and simply putting x in. So I have x cubed minus 4x all over h, not forgetting the limit. So this will give me the the derivative function, and then I can use that to find the slope. So this will equal the limit as h approaches 0 of, using Pascal's triangle or binomial theorem or any of that stuff, when I expand this out, I get x cubed plus 3x squared h plus 3xh squared plus h cubed, and then distributing the negative 4, I get minus 4x minus 4h, all minus, bring down the x cubed minus 4x, all divided by h. And in here, some stuff cancels out. The x cubed cancel. The negative 4x's cancel. And so here's the sort of trick. I guess I didn't point this out in the last slide. The problem with evaluating this limit is I'm dividing by h, and h is approaching 0. So I can't just substitute in 0 because that would be undefined. So I need to somehow get to a point where I can either factor this out or get to a known limit. In this case, I'm going to be able to divide out this h just like last time. So now we are at the derivative equaling the limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed minus 4h all over h. And I'll do it the other way this time. So I see everything has a factor of h. So instead of just going through the process of factoring out then dividing, I'll just divide straight away. So divide this by h, divide this by h, divide this by h, and divide this by h. And so I get the limit as h approaches 0 of 3x squared plus 3xh plus h squared minus 4. And as h approaches 0, these two terms go to 0, and I'm left with 3x squared minus 4. And now you have to be careful. I've seen a lot of students mess this up. This is the derivative function. I use it to find the slope, but it isn't the slope itself. So I actually need to evaluate dy dx at x equals 1, which is going to be 3 times 1 squared minus 4, which is negative 1. And now I can finally write down my lines. So my tangent, I'm just going to use point slope form. Y equals, let me make sure that's negative 1. We see that. So y equals slope times x minus the x coordinate plus the y coordinate. And normal, I have everything the same except the slope is the opposite reciprocal. The opposite reciprocal of negative 1 is positive 1. So I have y equals 1, x minus 1, minus 3. And let's look at this graphically to make sure it makes sense. So get rid of these, which was our old example. And now consider this function. Here's my graph. And my tangent line over here at 1, negative 3 is this. Looks good to me. Again, tangent here doesn't mean it doesn't hit somewhere else. And then my normal line should be perpendicular, and lo and behold, there it is. Alright, feel free to comment below if you have any questions. I hope this helped out.